Every year, landslides kill more than 4,000 people. Every year, they displace hundreds of thousands more, bury highways under millions of tons of rock and debris, sever rail corridors that carry the economic lifeblood of entire nations, and erase communities that took generations to build in seconds. In the time it takes you to read this sentence, somewhere on this planet, a hillside is moving. The forces involved are almost incomprehensible in their scale. A single major debris flow can mobilize 50 million cubic meters of rock, soil, and water, enough material to fill 20,000 Olympic swimming pools, and deliver it downslope at velocities exceeding 90 kilometers per hour. Nothing in the path survives. Not roads, not bridges, not buildings, not people. And yet, engineers fight back. In the mountain corridors of Switzerland, Japan, Norway, and China, on the steep faces of the Andes and the Himalayas, on the rain-saturated hillsides of California and the earthquake-prone slopes of New Zealand, a global engineering discipline has emerged over the past half-century that does something the untrained eye would consider impossible. It stops mountains from moving. The methods involve drilling steel tendons 30 meters into solid bedrock at 60 bar of hydraulic pressure. They involve injecting pressurized cement grout into fracture networks invisible to the naked eye. They involve anchoring wire rope meshes across cliff faces so vast that the cables alone weigh thousands of tons. They involve constructing reinforced concrete retaining walls the height of 10-story buildings against slopes that exert lateral pressures of 800 kilonewtons per square meter. This is mountain stabilization, the billion-dollar engineering discipline that stands between civilization and the raw geological violence of the unstable Earth. Join QuitTech Process as we uncover the secrets behind this engineering marvel. The cost of letting mountains move. Before a single anchor bolt is drilled, before a single meter of drainage tunnel is excavated, the engineers and governments responsible for slope stability face a financial calculation that is simultaneously enormous and unavoidable. The United States Geological Survey estimates total landslide damage costs in the United States alone at between $3.5 and $5 billion annually. Japan, a nation of exceptional geological violence, where 70% of the total land area consists of steep mountainous terrain and where 20% of all global landslide events occur, spends approximately 2 trillion yen per year on slope disaster prevention. That is 14 billion US dollars per year in a single country. In Switzerland, where the Alpine road and rail network is the economic backbone of Central European transit, a single major rockfall or debris flow event that closes the Gotthard corridor, the critical north-south axis carrying 20 million tons of freight and 1.2 million truck transits annually, costs the Swiss and European economy an estimated 1 million euros per day of closure. The engineering investment required to prevent that closure is, by any rational economic calculation, self-funding within a very short period. But economics, as consequential as they are, do not capture the full picture. The deeper driver of mountain stabilization investment is not financial. It is the basic obligation of government to protect human life. The Vajont dam disaster of 1963, in which a 260 million cubic meter landslide struck the reservoir behind an Italian dam, generating a wave that killed 1,910 people in the valley below, was not a failure of dam engineering. The dam survived intact. It was a failure of slope stability engineering. The slope had been moving at measurable rates for months before the catastrophic failure. The instruments detected it, the engineers saw it, and still, the mountain moved. That event fundamentally changed the discipline. It established in the minds of every geotechnical engineer who has studied it since a principle that drives every design decision in slope stabilization. The cost of intervention is always lower than the cost of failure. Always. Even when intervention costs hundreds of millions of dollars, it is cheaper than the alternative. The global slope stabilization market was valued at $12.8 billion in 2023 and is growing at 6.2% annually, driven by climate change increasing precipitation intensity in mountainous regions, urbanization pushing development into previously avoided steep terrain, and aging of existing slope protection infrastructure that was installed in the 1970s and 1980s and has reached the end of its design life. The mountain stabilization industry is not a niche specialty. It is one of the fastest growing sectors in civil engineering globally. How engineers stop a mountain. Mountain stabilization is not a single technique. It is a layered system, a hierarchy of interventions deployed in combination, each addressing a different failure mechanism, each contributing to a cumulative resistance that the destabilizing forces of gravity, water, and seismic energy cannot overcome. Understanding the complete system requires examining each layer in sequence. Stage 1. Investigation. Reading the mountain. No stabilization program begins with a drill or an excavator. It begins with months of investigation, the systematic effort to understand a slope's geometry, geology, groundwater behavior, and failure history before any engineering response is designed. Slope investigation begins at the surface. LiDAR surveys conducted from aircraft or drone platforms equipped with laser scanning systems accurate to 5 centimeters over areas of several square kilometers produce three-dimensional terrain models that reveal the subtle topographic signatures of previous landslide activity. Scarps, hummocky terrain, tension cracks, deflected drainage channels. Features invisible to the naked eye become unmistakable on a LiDAR-derived digital elevation model. Below the surface, the investigation deploys boreholes, typically 75 to 150 millimeters in diameter, drilled to depths of 20 to 60 meters, depending on the suspected failure plane depth. Within each borehole, inclinometer tubes are installed, precision instruments that measure the lateral deflection of the borehole wall at 500 millimeters intervals, using a torpedo-shaped probe lowered through the tube on a calibrated cable. Deflection measurements accurate to 0.02 millimeters per meter of depth reveal the exact depth, orientation, and rate of movement of the failure plane within the slope. Piezometers installed in these same boreholes measure groundwater pressure at the failure plane, often the single most critical parameter controlling slope stability. The collected data feeds a geotechnical model, a three-dimensional numerical representation of the slope's geometry, material properties, and groundwater conditions, analyzed using limit equilibrium or finite element methods. The analysis yields a factor of safety, the ratio of the forces resisting slope movement to the forces driving it. A factor of safety of 1.0 means the slope is at the point of failure. Design targets for stabilized slopes in critical infrastructure locations typically require a factor of safety of 1.5 or higher, meaning the stabilization system must provide 50% more resistance than the minimum required for stability.
Stage 2. Dewatering, removing the engine of failure. Water is the primary driver of most landslides. It adds weight to the slope, reduces friction on the failure plane by increasing pore water pressure, and in freeze-thaw environments generates hydraulic pressures as it expands on freezing. The single most cost-effective stabilization intervention for most slopes is therefore not a structural system, it is a drainage system. Horizontal drain holes, typically 75 to 100 millimeters in diameter, drilled at 5 to 10 degrees upward inclination into the slope at depths targeting the saturated zone above the failure plane, can reduce pore water pressures by 30 to 60% at the failure plane. A slope that requires 8 million euros of structural reinforcement to achieve the target factor of safety with full groundwater pressure may achieve the same target with drainage alone at a fraction of the cost. Drainage is always investigated first. For slopes where horizontal drains are insufficient, drainage tunnels are deployed. Full-size accessible tunnels, typically 3.5 meters diameter, excavated horizontally through the slope at the critical drainage elevation. From the tunnel, drain holes are drilled radially at 15-meter spacing, creating a comprehensive groundwater interception system that can reduce piezometric levels across the entire unstable mass. Switzerland's slope stabilization program has constructed over 200 kilometers of drainage tunnels in alpine slopes since 1970, more drainage tunnel per kilometer of mountain than any other nation on Earth. Stage 3. Ground anchors, nailing the mountain to itself. Where drainage alone cannot achieve the required factor of safety, the next intervention layer is ground anchors, high-capacity steel tendons drilled and grouted into stable rock or soil below the failure plane, applying a direct tensile force that increases the normal stress on the failure surface and thereby increases the frictional resistance to sliding. A typical rock anchor for slope stabilization consists of a high-strength steel tendon comprising 91 individual 7mm wires stranded into a 150mm diameter bundle, inserted into a borehole drilled at the design angle, typically 10 to 25 degrees below horizontal, to optimize the anchor force direction relative to the failure plane, then grouted in place with cement grout pumped at 10 to 20 bar pressure through a grouting tube to ensure complete bond between the steel tendon and the surrounding rock. The free length of the tendon, the unbonded section between the anchor head at the slope surface and the bonded zone in competent rock, passes through the unstable zone without bonding to it, allowing the unstable mass to be loaded against the stable rock without the anchor taking bending loads. Once the grout has achieved full strength, typically at 28 days, with a minimum characteristic strength of 35 megapascals, the anchor is stressed to its lock-off load using a hydraulic jack. For a 12-strand, grade 1860 megapascal pre-stressing steel anchor, the typical lock-off load is 1200 kilonewtons per anchor. A major slope stabilization project may install 500 to 2,000 such anchors, each carrying over 1,000 kilonewtons of preload, creating a combined restraining force measured in hundreds of thousands of kilonewtons bearing directly on the failure surface. Stage 4. Soil nailing and micropiles, the steel skeleton. For slopes in soil rather than rock, and for the shallow failure mechanisms that ground anchors may not address, soil nailing provides reinforcement through a different mechanism. Not pre-stressed tendons pulling the slope toward stability, but passive steel bars, typically 25 to 32 millimeter diameter ribbed reinforcing steel, 6 to 12 meters long, drilled and grouted at 1.5 to 2.0 meter centers on a grid pattern across the slope face. Soil nails do not apply a preload. They work in tension only when the soil moves. The nail resists the movement by mobilizing its bond with the surrounding soil, transferring the tension force to the nail and from the nail through the facing structure into the stable zone. A typical soil nail wall for a 10-meter high slope uses 200 nails at 1.5 meter horizontal and vertical spacing, each 9 meters long, grouted with cement grout at 5 bar pressure, connected at the face by shotcrete facing 100 to 150 millimeters thick, reinforced with welded wire mesh. The completed structure can resist slope failure pressures of 150 to 300 kilonewtons per square meter, comparable in structural performance to a conventional retaining wall at a fraction of the construction cost. Stage 5. Rockfall protection. Catching what cannot be stopped. Some slopes are too steep, too fractured, or too active for anchoring or nailing. Individual rock blocks on near vertical cliff faces cannot be reliably stabilized. They can only be contained when they fall. This is the domain of rockfall protection systems, engineered barriers and nets designed to intercept falling rock and absorb its kinetic energy without allowing it to reach the protected infrastructure below. The most dramatic element of rockfall protection is the high-energy barrier, a system of steel wire rope nets supported on steel posts and anchored to the slope, designed to absorb the kinetic energy of impacting rock blocks without structural failure. The most advanced barriers in current use, developed by Swiss manufacturers including Geotechnical and Trümer, can absorb impact energies of up to 10,000 kilojoules, equivalent to a 100-ton rock block falling at 50 meters per second. The energy absorption is achieved by a system of ring nets, spirally wound wire rings, each 300 millimeters in diameter, connected in a flexible mat, and energy-absorbing brake elements installed on the supporting ropes, which deform plastically under load to dissipate energy without transmitting peak forces to the anchors. A single 100-meter wide, 6-meter high barrier of this specification contains 15,000 wire ring elements and 80 brake elements, each tested individually to ISO 17745 standards before installation. The steel giants of slope stabilization. The machinery of mountain stabilization operates in some of the most extreme environments on Earth. These are not flat ground construction sites with level pads and organized access roads. They are near vertical cliff faces, steep debris flow channels, unstable slope terraces barely wide enough for a single machine, and underground tunnel faces where the rock may be moving at the moment the drill advances.
The drilling rigs that install ground anchors and soil nails in steep terrain are engineering marvels of compact power. The Atlas Copco Smart Rock T40, a 15-ton crawler-mounted drill rig capable of operating on slopes up to 35 degrees, delivers 25 kilonewtons of thrust force and 3,200 newton-meters of rotation torque to the drill string, advancing through hard rock at 30 to 50 millimeters per minute to drill the 75 millimeter diameter holes required for rock anchors. On slopes too steep even for tracked rigs, rope access drilling systems deploy 600-kilogram pneumatic drifters on wire rope suspended from anchor points at the crest. The drill operator working on the cliff face in a harness, the drill advancing 25 millimeters per blow at 1,800 blows per minute. For drainage tunnel construction, the Sandvik DT922i twin-boom electro-hydraulic jumbo drill, a 55-ton steel giant that occupies the full profile of a 3.5-meter tunnel, advances the tunnel face by drilling 48 blast holes in a precisely calculated pattern, each 45 millimeters in diameter and up to 4.5 meters deep, loaded with an FLO explosive at 0.8 kilograms per meter, then fired in a millisecond delay sequence that fractures the rock in a controlled cone while directing the blasting energy forward and minimizing vibration in the surrounding mass. Each blast round advances the tunnel 3.8 to 4.2 meters. The excavated material, typically 25 to 35 cubic meters of broken rock per round, is removed by a fleet of 10-ton underground dump trucks operating in the completed section while the next round is being drilled. The installation of major rockfall barriers on near-vertical alpine cliff faces requires machinery that can operate where no road exists. Helicopter-supported construction teams use EC-145 utility helicopters with a 1.4-ton external lifting capacity to transport steel posts, anchor hardware, and wire rope coils directly to the installation positions on the cliff face, with workers in harnesses assembling the system by hand from rope access positions. A single 100-meter barrier section on a vertical cliff face requires 120 helicopter cycles and 800 person-hours of rope access labor. Engineering against geology, gravity, and water. Mountain stabilization engineers do not choose their working environment. The mountain chooses it for them, and the mountain's choices are rarely comfortable. The Norwegian Road Administration's slope stabilization teams work on cliff faces above Norwegian fjords, where winter temperatures reach minus 25 degrees Celsius, and the
rock face is coated in 50-millimeter thick ice sheets that must be cleared before drilling can commence. The Japanese Nexco highway slope teams work on hillsides where typhoon season rainfall can deliver 300 millimeters in 24 hours, filling drainage systems faster than they can discharge and driving piezometric levels to their annual peaks in hours. In the Himalayan region of Bhutan and Nepal, road slope stabilization operates at altitudes between 2,000 and 4,500 meters above sea level, where drill rig diesel engines lose 30% of their power output due to reduced atmospheric oxygen. Workers experience altitude sickness above 3,500 meters, and the monsoon season imposes a 4-month construction stoppage every year as rainfall exceeding 500 millimeters per month makes slope access impossible. The geological environments are equally hostile. In the Swiss Alps, slope stabilization projects regularly encounter rock masses with rock quality designation values below 25, meaning that more than 75% of the drill core is returned as broken fragments rather than intact cylinder, indicating a rock mass so fractured that each drill hole collapses before the anchor can be inserted, unless the hole is cased with steel pipe throughout its length. In coastal California, Monterey shale slopes present expansive clay minerals that swell on contact with cement grout, exerting pressures up to 200 kilonewtons per square meter on anchor hardware, requiring specialized resin anchoring systems that do not rely on cement hydration. Against all of these challenges, the cold, the altitude, the rainfall, the fractured rock, the swelling clays, the engineers advance. Not boldly, not recklessly, methodically, with instruments and data and calculations refined by decades of practice, replacing what was understood imperfectly with what is now known precisely. The mountain that will not move. There's a profound reversal at the heart of mountain stabilization engineering. The mountain, geological time expressed in rock and soil and water, has been moving since before human civilization existed. It will continue moving long after human civilization has ended. The engineer arrives for a human lifetime, drives steel into bedrock, injects cement into fractures invisible to the naked eye, and says, "Not today, not here, not while this road needs to stay open and these people need to stay safe." And remarkably, astonishingly, it works. The La Clapière landslide in the French Alps has been moving for over a century. A stabilization program involving 150 ground anchors, a 2.4-kilometer drainage tunnel, and continuous real-time monitoring by 200 sensors has reduced its movement rate from 2 meters per year to 0.3 meters per year and protected the town of Saint-Étienne-de-Tenay and its 1,400 residents from the 55 million cubic meter mass above them. The Ruinon landslide in Italy's Stelvio National Park, 10 million cubic meters of unstable debris threatening the Val di Peo Valley below, has been held to acceptable movement rates by a drainage tunnel and anchor system that cost 45 million euros. The alternative cost, in human lives and destroyed infrastructure, was incalculable. Japan, the world's most aggressive practitioner of slope stabilization engineering, has installed over 3 million ground anchors across its national slope protection program, more than any other nation, and has reduced slope disaster fatalities from over 700 per year in the 1960s to below 100 per year today, despite a steady increase in extreme precipitation events driven by climate change. The engineering has outpaced the changing climate. So far. The global slope stabilization industry continues to evolve. Machine learning algorithms now analyze inclinometer, piezometer, and weather data from monitored slopes in real time, predicting failure probability hours or days before it would be visible to human observation. Fiber optic strain sensing cables installed along critical slopes can detect millimeter-scale movements across kilometers of hillside simultaneously. Remotely operated drilling rigs remove human operators from the most dangerous installation environments. The mountain is still moving. It always has been. But somewhere below the surface, in the bedrock that has been there since before the mountain had a name, 91 high-strength steel wires hold their tension. The cement grout has set. The drainage tunnel is discharging. The instruments are reading. The engineers are watching. The mountain will not move today. And tomorrow, the engineers will be back. For more engineering marvels defending civilization against the forces of nature, subscribe to QuitTech Process. The secrets of extraordinary construction are waiting, and we will uncover every single one of them.